Today I'm going to be going through the Pre-Calculus Unit 1 test review. The test is entirely no calculators, so keep that in mind as you're going through this review. So the first thing we're going to do is graph a piecewise function. So remember, these are the different areas where these lines are going to be represented. So we have something for when x is less than -2, something when x is -2, from -2 to 4, and then past 4. So each of these areas is going to have a graph. The first one, -2x minus 3, when x is less than -2. So a couple options. We can start down 3. A slope of -2 means it's going down this way, and go up, over, and start our graph there. Or you can actually plug in -2. If I plug in -2, I get 4 minus 3, which is 1. So that gives us that with an open dot. Okay, at -2, we have a point at -4. From -2 to 4, we have x plus 3. So y-intercept of 3, and then a slope of 1. So it's actually going to end there. 2, 3, to 4 with an open dot. And then 1/2 x minus 2 when x is greater than 4. So again, we can start at -2 and just go with a slope of 1/2 until we get to 4, or if I plug in 4, half of 4 is 2 minus 2 is that 0. That will be a closed dot. And then an arrow on the end because we don't have an ending value there. Then we're going to evaluate. So you can either use the graph or the equation. -4, we're up at 1, 2, 3, 4, up at 5. Or you plug it into the top equation. At -2, we're at that -4. At 2, we're at 5, or again, plug it in there. And then P of 4 is right there at 0. Defining a piecewise. So you can have f of x equals, we've got 1, 2, 3, 4 different line segments. So I'm going to start with my domains. The first one's going from -5 to -3. So -5 is less than or equal to x is less than 3. We have this -3. We have a dot when x is equal to -3. We have a line segment from, sorry, there should be -2. Okay, we have a line segment from -2 to +2. And then from 2 to 4. Now this 2 could have been included on this line or this line. So this inequality or this inequality could be inclusive. Now we're looking at the equation of the line. This one has a slope of -1. So -x, and then if I continued it, it would cross at -2. At -2, we're up at 3. From -2 to +2, it has a slope of +1/2. And it crosses at -2. And then the last one has a slope of 3. And if we were to continue going down, so we're at -1, this would be at -4, this would be at -7. Our next one again has 4 parts. Going from -5 inclusive to -2 non-inclusive. Something when x is -2, -2 to +1, both open dots, and then the last segment goes from 1 to 4. Okay, then we're going to find the equations of the lines again. So this one has a positive slope of 1 and would cross at 3. Here we're at 3. This has a slope of -1, y-intercept of -1. This one has a slope of 2. And if we went back, this is at -4, go over and down, we'll be at -6. Okay, so now we're going to be graphing using some symmetry. So we have the point R, which is at -3, 4. Okay, there's R. Okay, and we're going to graph a point so that R and S are symmetric to the x-axis. So if there's a point here, there's a point here, S. Those coordinates are -3, -4. Y-axis is going to be over here. That's at 3, 4. The line y equals x. The x and y values are going to switch, so it's going to be at +4, -3. Y equals -x, they're going to switch and become opposite. So that's going to be at -4, +3. And you can also draw those lines in there. R and W are symmetric to the origin. So I'm going to go to the origin over 3 down 4 and repeat that over 3 and down 4. That is W at 3, -4. Okay, symmetric to the point 1, 2. So I'll go ahead and do 1, 2. And if it's going to be symmetric to that one, just like I did with the origin, I'm going to stair step. So we're going over 4, down 2. So I'm going to go over 4, down 2. So that's at 5, 0. And then the point -4, -2. So this one we're going to stair step. So I'm going back 1, down 6, and going back 1, and down 6. The coordinates for that are -5, -8. For this next section, we're determining if the function is even or odd. The work that we're going to show is plugging in -x, and then the symmetry, okay, if the function is even, it's symmetric to the y-axis. If the function is odd, it is symmetric to the origin. Okay, so here, we're going to plug in -x. If I have a -x and I square it, it becomes positive. So this becomes the same as what we just started with. Okay, if it starts the same, if f of -x equals our original function, then our function is even, and therefore symmetric to the y-axis. Okay, letter B here. F of -x is going to be 5 minus 3 times -x squared plus -x to the 4th. So we get 5 minus 3x squared plus x to the 4th, which is equal to f of x, which means it is even and symmetric to the y-axis. Plug in -x, we have -x to the 5th minus -x cubed minus a -x. This is going to stay negative, so negative makes that one positive. Same thing here, we're going to have a positive x, and same thing here. Okay, this is the exact opposite of what we started with. Okay, f of -x equals the exact opposite. That one changed, that one changed, that one changed. So this one's going to be symmetric to the origin. Our last one here. So this one becomes opposite, but this one stays the same. So this is neither. They either all have to stay the same or all become opposite in order to be even or odd. Okay, if the point -4, 7 is on the graph, what other point must be on the graph? Okay, well, thinking about the symmetry, if the point -4, 7 is on here, there has to be one on this side of the y-axis, which means we have a point at 4, 7. If it's odd, it's symmetric to the origin, so that -4, 7 is going to have a counterpoint at 4, -7. Okay, for number 6, finish the graph if the function is even, which means it's going to be symmetric to the y-axis, so I'm just going to reflect this over. If it is odd, okay, it's going to be symmetric in the origin. So there's going to be a 0.33 here, 0.33 here. So this is going to look like this. And then you could just trace the point if you're not sure how this is going to look. So this is what, at 9, up at 1, 2, 3, 4, 5, 6. So we're going to go back 9 and down 6. Like that. It's also going to look the same if you flip it upside down. In this next section, we're going to describe the behavior of the function. So we're going to classify the extrema, the maxes and mins, and classify them. That's going to be a coordinate. We're going to describe the end behavior, and that's going to be using limit notation. And we're going to describe the intervals, the x values, where the graph is increasing and where it is decreasing. So this first one, you need to know how to graph it without a calculator. So this is a parabola moved to the right 2. Here, 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 4. First up is the extrema. There is 1. There is a 2, 0 is an absolute maximum. And you can abbreviate like that. Okay, end behavior. Using limit notation, we're always going to look at the limit as x goes to infinity and the limit as x goes to -infinity. For both of these graphs are increasing without bound, so they're going to be going to infinity. Increasing and decreasing. So this graph, at first glance, you want to say it's always increasing because the arrows are going up. But remember, we're always reading it from this direction to this direction, so it goes down, then goes up. So it's increasing from 2 to infinity, or you can just say x is greater than 2, and it's decreasing from -infinity to 2. Okay, next one. The extrema, this one has 2, a minimum and a maximum, and they are both relative. So -2, -3 is a relative minimum. 0.11 is a relative maximum because they're both values less than this one and greater than this one on the graph. Our end behavior as we go to positive infinity, our graph is going down to -infinity. As we go to -infinity, our graph is going to positive infinity. Okay, increasing and decreasing. This graph is increasing from here to here, so from -2 to 1. It's decreasing from -infinity to -2, and then decreasing past 1. So 1 is less than x is less than infinity. This graph has 3 extrema. At -3, 2, we have a relative max. At -1, -1, we have a relative minimum. And then at 1, 3, we have an absolute max. Our end behavior. As we go to infinity is going to negative infinity, and as we go to negative infinity is going to negative infinity. Okay, this graph increases, decreases, increases, decreases. So from negative infinity to 3, it's increasing. From -3 to -1, our graph is decreasing. From -1 to 1, it's increasing, and then from 1 until infinity, it is decreasing. Okay, so this next section we're going to be doing a bunch of different graphs. So we have 6 parent functions, and then we're going to be manipulating them in different ways. The first parent graph that we're going to be using is the absolute value of x. So 0, 0, 1, 1, 2, 2, 3, 3. Looks like a V. Next is the absolute value, but we're multiplying it by a -3. The negative is going to reflect it over the x-axis. The 3 is going to stretch it vertically. So this graph, rather than going over and down 1, it's going to go down 3. This one, the 1/2 on the inside, means it's going to be stretched horizontally. So it's going to have a slope of 1/2 on this one. This one in particular, it actually doesn't matter if it's on the outside or the inside. It'll look the same. Okay, this one is going to be our absolute value moved to the right 4 and up 2. So the right 4, up 2, but no stretching this time, just our regular V. Our next parent graph is the step function, the greatest integer function. So this one, we have closed dots on all the integers. So 1, 1, 2, 2, 3, 3, -1, -2, -3. And then it's a horizontal line to an open dot. This one, we are multiplying by a number less than 1 on the inside. So this is going to be stretched horizontally. So for this one, we're going to start at 0, 0, but this first bar is going to be 3 units long before it jumps up to the next one. 3 units long, 3 units long. This next one is going to take the bars, it's going to reflect it over the x-axis, so the steps are going to be going down, and then it's going to be stretched vertically. So the first one's still going to be at 0, 0, have a length of 1. The next one, though, is going to be down here at -4, and then there's going to be one over here, like that. X squared is our next parent. So 0, 0, 1, 1, and then over 2, up 4. So those 5 points are what I'm going to be looking for. This +3 on the inside is going to move our parabola to the left 3 units. This one is going to take our parabola, reflect it over the x-axis, and move it up 4. So it's going to start up here at 4, then go down 1, and then down like that. Our next parent is the square root of x. For the square root, we're at 0, 0, 1, 1, and 4. The square root of 4 is 2. So these 3 points are what I want to see. There is no bottom half. It is just that top half there. This one's going to be shifted to the left 4. 1, 2, 3, 4, and then going to be stretched vertically by a factor of 3. So instead of going over 1 and up 1, our next point's going to be at 3, and instead of going over 4 and up 2, we're going to be at 6. Now we have it where we're going to be moved up 3, and then it's going to be reflected over the x-axis. So instead of going over 1 and up 1, we're going to go down, and then over 4 and down 2. Our last parent function is 1 over x. So 1 over x, I start at 1, 1. 2 is going to be at 1/2. 1/2 is going to be at 2. And then it's going to approach each of the x and y axis. Same over here. Two over x is going to stretch the graph vertically. So instead of having a point at 1, 1, it's going to be at 1, 2. Instead of 2, 1/2, it's at 2, 1. Instead of being at 1/2, 2, it's going to be at 4. Still approach the x and y axis, and then the same in the third quadrant. Here, this is going to be moved to the right 2 and up 3. So anything you're adding or subtracting directly is going to move the graph left and right. So this is going to go right 2. And we're adding this after the fact. So it's going to be up 3. So those are going to be my new vertical and horizontal asymptotes. So then I'm just going to do the 1, 1, 2, 1/2, 1/2, 2 from that. And down here. Alright, so this one's kind of interesting, and we did one like this in class. The parent function here is actually the x squared, and what I'm going to do is do x squared minus 4, which would be a parabola down 4, over 1, up 1, 4, and so on. And then over 3 would be up 9, so, up here. So we have this graph, and I'm just doing a dotted line. Okay, but then we're taking the absolute value of that. So this part of the graph is going to stay the same, and this part of the graph is going to stay the same. This part is going to get bounced up. Like that. Right, our last topic is of inverses. We're going to graph the function and its inverse. We're going to find the inverse, and then we're going to state whether the inverse is in fact a function or not. So for the graph, and you can either graph it, then find the equation, or you can find the equation and graph it from there. So if I graph 2x minus 5, so 1, 2, 3, 4, 5, slope of 2. So this is h of x. The inverse is going to switch x and y coordinates. So instead of being at 0, -5, we're going to be at -5, 0. Instead of being at 1, -3, we're going to be at -3, 1. Instead of being at 2, -1, we'll be at -1, 2, and so on. It's a reflection in the line y equals x. This would be the inverse h inverse of x. Okay, now we're going to find the inverse equation. So I'm going to switch x and y. So I'm going to say x equals 2y minus 5, and then solve for y. So I'm going to have x plus 5 equals 2y, and then divide by 2. So 1/2 x plus 5 halves equals y. That is our inverse, and that matches our graph here. We had a positive slope of 1/2, and this y-intercept is at 2.5. You could also write this as x plus 5 over 2 if you want to. Those are both completely legitimate. Is this a function? Yes, it is a function. It passes a vertical line test. Right, x minus 2 squared. Move to the right 2. The inverse, those x, y values are switched. F of x. So the inverse, instead of being our vertex being at 2, 0, we're going to be at 0, 2. Instead of being at 1, 1, we're still going to be at 1, 1. And instead of being at 3, 1, we're going to be at 1, 3. 0, 4 is going to be at 4, 0. And then there's going to be 1 at 4, 4. Okay, so there is our inverse. The equation, so I'm going to switch x and y. Take the square roots. This is going to be plus or minus the square root of x equals y minus 2. So add the 2 over. 2 plus or minus root x equals y. That is our inverse equation, okay, which is not a function. So if we wanted to make it a function, we would have to restrict the domain in order to do so. Lastly, we are going to determine whether the two equations that we are given are inverses using the definition of an inverse. And the definition of an inverse is that f of g of x and g of f of x equals x. So we're going to do those compositions. F of g of x. That's going to be f of this. X over 3 squared minus 1. Then we're going to take that whole thing and plug it in for this x. So we're going to have 3 times the square root of this x is now x over 3 squared minus 1. Then we have that plus 1. Okay, well, plus 1 minus 1, those go away. Okay, the square root and the squared go away. And then the 3 on top and the 3 on the bottom cancel, and we have x. So this direction is verified, but we do want to double check. And we do have this restriction. So g of f of x is 3 root x plus 1. And we're going to take this and plug it in for this x. So 3 root x plus 1 over 3 squared minus 1. Okay, the 3's are going to cancel. So we have the square root of x plus 1 squared minus 1. So the square root and the square will again cancel. When we get x. Again, when we have this restriction, when x is greater than 0, these will be inverses, because this would only be half of the parabola, if you think about it like that. All right, let's do this last one. So f of g of x is going to be f of 2x minus 12. Well, that's going to be 1/2 times 2x minus 12 minus 6. So 1/2 of 2x is x. 1/2, we have a minus 6. Minus 6, which gets us x minus 12. That is not x. These are not inverses. Okay, so good luck on your test.